So I have three pieces to return to you. Sorry that I made you walk here 3 times. I did some computation of the complexity, big O, that would take to put all this together, and was many hours of work. So it's very good to know these things, because I would have started at some point to say this. Oh, this is a calculator. This is a terrible idea. So sorry that I told you here 3 times, but this is the most efficient way to do it. So I'll start with this one and I'll finish with the. So make sure I understand your name. These are 2 homework and the midterm. So everything will go back to this. We are finally catching up everything. And there was no this morning. Ming Liang, thank you. Make sure I hear your name. James Kramer. Daniel Dureka.
Yeah.
Thank you. Achenbach. Belen. Ray Emory.
Here.
Thank you. Morgan Kate.
Here.
Thank you. Poonam Rani. Thank you. Frank San. Sanjay K.
Here.
Thank you. Jeffrey Becca.
Here.
Stephen Johnson.
Here.
Tim Coutinho.
Yeah.
Jacob Collins.
Here.
Cameron.
Here.
Lee Hong.
Here.
Everyone is here today. Grady Cook.
Here.
Bailey Johnston. Mel Flyer.
Here.
Thank you. Sam Bernada. Benjamin B. Benjamin. No Benjamin. Yes. Wait. Dennis M. Davud Alavi. Davud. Huang Kim. Kim. Here. He's not. Lambert. What are you trying to do there?
My homework.
It's here, on this chair.
Yeah.
Tristan, Amonetti. Huang Sang Su. Thank you. Cody W.
Here.
Thank you.
Yes. Sam John Lee. Andrew Gonzalez. Ronnie Song. Yeah. Lee here. Yogi S. Yogi S. Carson. Andrew Wyatt.
Here.
Thank you. Nick Gilbert. Victor C. Victor. Donald Ransfeld. All right, we got rid of one. Now the other. David Ross. Rodion. Jason Yang. Frank San. Ray Emory.
Here.
Sam Bernaza. Benjamin B. Sam Brook. Thank you. Jeffrey Becker. Wait. Robert Longacre. Robert. John M. Hannah Fleming.
Here.
Thank you. Jimena. Cameron. And Juan Xian Su. Carson. Lee Hong.
Here.
Thank you. Sunan S. Santivel. Morgan K. Keith McGuinness. Poonam Rani. Daniel Dureka. Nick Gilbert. Joel Sester.
Here.
James Kramer.
Here.
Daniel Persson.
Here.
Jacob Collins.
Here.
Jeremiah Pesca. William Newcomb. Andrew Gonzalez. Yogi Saputa. Ronnie Song. Sanjay K.
Here.
Bailey Johnson. Steve Coutinho. Cody W.
Here.
Fantastic. So I don't know if I read it or not. You get it. All right. The meter. Jano Shakerbach. Tristan. Michelle Alajami. Michelle. Dawood Alawi. Faisal. Abdullah A. Benjamin B.
Yep.
Roland B. Emily Becker. Jeffrey Becker.
Here.
Sandro. Ivan Burnham, Ivan Bennett, Victor C. Wait. Anthony Chin.
Here.
Duanil Chosky. Cole Coffer.
Here.
Jacob Collins.
Here.
Carson. Tim Coutinho.
Yeah.
Lily Cox. Waylon Cood. Bobby Davis. Anirudh Didavi. David Ross. Daniel Dureka.
Yeah.
Gabriel Edwards.
Here.
Michael Hart. Alexander L. Haji. Ray Emery.
Here.
Anna Fleming. Mel Flyger.
Here.
Jarvin Garcia. Nicky Gilbert. David Gilmore. Andrew Gonzalez.
Here.
Basel Hemiet.
Here.
Basel. Thank you. Spencer Hunt. Lee Here. Lee Hong.
Here.
Matthew Hubbard. Ivan Johnson.
Here.
Bailey. Brian Jones. Sanjay K.
Here.
James Kramer.
Here.
Jordan Kramer. German K. or V. German. Grady Cook.
Here.
Thank you. Connor Cole. Tiwo Kwong. Morgan K. Robbie Launder.
Here.
Do I read it right?
Yes.
Seung Jun Lee. Robert Longacre. Kim Ma. Alexander Mason. Ian McBride. Ian. Carl. Pete McGuinness. Denis Mezanovic. James Moore. John Armolen. Mira Murali. Cameron N. Sohail N. William Newcomb. Yijid Sen. Poonam Rani. Daniel Person.
Here.
Jeremiah Pesta. Kevin Fan.
Here.
Ashley Powell. Rodio. Elijah. Sean Robert. Mina. Sunan Santivel. Yogi. Oh, Yogi.
Yeah.
Joe Sester. Austin Chia. Alexander Shelby. Robert Short.
Here.
Ronnie Song, Juan Chiang Su, Frank San, Andy Veruca, Millian Miller, Cody Weibo, Amanda Williams, Carissa Wood, Andrew Wyatt, Jason Yang. You're welcome. Yes. So do I have more homework? Let's see what the website says. This is about trees. So says homework assigned. We put some notes in the previous one because we were falling behind, but now we are on perfect schedule. Homework? Yes, thank you. All right, so it's good that finally we caught up and we are on schedule. Oh, I get some question about the grades. Yeah?
Yeah, if your average is above 100, since you graded, there's a lot of questions and you grade 10. If your average is...
So it's explained here. Sorry, wrong page.
You cap it at 100.
Yeah, say that your average is scale, so it's perfectly clear. You get more than 100.
Okay.
It's written there.
Scale plan, so I was curious.
I'm sorry?
You wrote the scale plan, so I was wondering if it was capped at 100.
No, it doesn't say that.
Yeah, scale to 100 means that either above 100, it's scaled down.
Well,
Compared to if you said.
all right, so you can get more than 100. You're lucky day. So, some people seem confused by the rule that you can skip homework, but all the homework is graded. So this is a very gentle and kind rule for people that for one reason or another cannot submit homework. So it's not panic, it's not a disaster, it's not going to ruin your grade. And throughout the term, it's very possible that one day you are sick or you couldn't prepare for the lecture because you had to do something else that was more important, and so you skip it. Everyone is fine. If you submit it, we grade it. And some people seem very upset with this. If someone wants to tell me why, I may try to address it. Yes?
One potential reason might just be like it's helpful to get feedback on it. But once
Yes.
you've submitted your 5 homeworks, maybe you don't want to risk lowering your grade by continuing to submit them to get feedback.
So, the goal is not to give you a higher grade when you know less. Because this would be the situation, right?
Yeah.
There is no moral justification for that. And so, if you submit it, I would also make a strategic consideration here. You can draw one question or two, right? So, considering that the entire homework count 1/2 of an exam, and you have 8 homework, so a couple of questions more or less really doesn't change anything. It seems much better to risk having a wrong question rather than not getting the feedback and not get right. So the bottom line is that the goal of counting 5 is not to give you a higher grade when you know less. One can always game the system, so one can use this rule to get maybe a higher grade, but this is not the point. Sometimes I say, look, we give to charity because it's good to be in a society where no one starves or no one is homeless or whatever. And of course, someone can gain this and say, instead of working, I get the charity and I enjoy my time. This is not a good reason not to give to charity. If someone gain the system, we can still live with that and do good for everyone else. So here is the same idea. This is to make the life easier for everyone. Yes?
I know a lot of people who use homework that I used to, and a lot of people didn't do it because they don't know the date on it.
So fantastic. And this is why we have this rule, because someone may misunderstand and still you are not penalized, or you are not penalized anyway.
So when you still want to turn it in,
Say it again.
when you still want to turn it in, but
We don't do it because we don't have the resources. You know, when I go back to the department, the grader get it and they start to grade. Now you want to put one in the pipeline in the middle when they are ready, put the grades in or whatever. It's going to take a tremendous amount of time for little benefit. There is no penalty it's given. So this is why we have this rule. Now, here I'm not sure why people didn't understand that this one was due. Because if we look at this one, in the week of February 27, we completed this one, and the homework was assigned, is written there. So how did people didn't understand this? There is never due date except for the time when we were falling behind schedule, so it was understandable. And I think the fact that the large majority of people thought it did, yes, I'll give you a chance to talk. Yes, Sam?
So, you have number 6 as the due date right next to the little link.
Because we were behind schedule.
See, well, and that's, okay, so that's ambiguous, I didn't know that. It didn't say
All right.
anywhere. So I was waiting
All
for
right.
the little number there, like this guy.
All right.
To
Yes?
see how that.
The biggest confusion for me was there was a homework that was due after the first midterm, that it wasn't due. And you said that if there's no due date on it, then it's not due. That was,
But when we were behind schedule, not when we had, why would we have a schedule then?
No, I think I was with him on the midterm piece, that I presumed because of the midterm existing, and I wasn't even looking at the due dates, I just was like, we had the
All right,
midterm,
so-
so it wasn't on my board firm.
There is no penalty, so we are all fine.
I'm just saying that's what confused me.
All right. Yes? Homework 4, question 7.
Yes.
Homework 4, question 7. Yes. So what's the question? The answer is A.
Oh, that's almost
I got it wrong.
One at a time. Summary. So was misgraded?
Yes.
All right. So send an email. Before sending an email, it's going to make any difference on the grade. Because you know, when you go to the thousands of the point, it's not going to make any difference. So we can change it. Say that again.
failing, it makes it.
every point counts.
All right. Every point counts. All right. Yes. Give everybody 1 point. This is not a bad idea because it will save a lot of. are talking here and I cannot hear. Speak loud.
The final coming up?
Yes.
When is our final day? I don't know. I looked it up last time on the course website. Like, is it the 15th or is it the following week during finals week?
It's during the finals week.
Okay.
Well, I think on the 15th we had class, right?
Yeah. Just on the schedule. So it looks like you allocate the entire week towards the review. Is that true?
Yes.
Okay.
So I think that now because we already spent half an hour on this and at the return, we may fall behind a little bit, but we still have this slide. Yes?
Can we go over to the notes?
Yes. So, maybe not all of it, but I don't have a copy here. I have to borrow yours. Thank you. All right, which one do you want to go over?
I was curious why 18 is bijective and not, or is not bijective, but is
So tell me, oh sorry, you are not seeing it. Tell me what was going on through your mind so I can really address the question, because otherwise I'm not sure I tell you this is the definition. So tell me a little bit more.
yeah. So if we have X and Y inside of a set, any old set, whatever, right?
Yes.
And then we have a function that maps some input to another input inside that same set, such that
From an input to an input, no. From an input to an output.
yeah,
Let's draw a picture to see whether it helps.
so the domain is the same code.
So here we have,
Say ABC.
so here this is A, this is B, this is F, right? So now I have two elements, X and Y. You can pick them any way you want, all right? And it turns out that f of x is equal to f of y only when these two are the same. All right? So the picture that I just draw is wrong. Because from the picture you will see that those two dots are different, but they go in the same.
Oh, that makes sense. Never mind.
All right?
I misread the question.
All right.
Thank you.
Yes, you're welcome. Any other question you are dying to see the answer for the meeting? Yes? Number? 26. All right. 26. This is the one that there is a link in the slides. Did you notice it? This is so well explained. So did you look at that or you missed it? Because I certainly cannot explain it better than is there. There is it's really beautiful. So what is this problem? This problem is 10, choose 3, right? You remember the formula? So I'm not sure what I should explain at this point, yes?
I think it's actually a combination with repetition, not choose K. So like 10 plus 3 minus 1, choose 3.
So let's do it. So here we have the 10 flavors, right? So we have a 10 plus 3 minus 1, 3. Are we saying this one? All right, so we computed. What is this one? Someone did it? 240. All right, I believe you. 220. All right. Any other question? So the second midterm went much better than the first. And this is the second time that I'm teaching this program, and it happened before. So the first time I thought it was a fluke, and now I think it's a rule. Can someone understand me why the second one, where there is more technical material, much more material? Yes, Cass.
I felt like it was a lot less ambiguous. Like I could actually go through the math problems instead of having to read three similar sounding definitions.
So, but the previous exam was different. So now is a fluke that the first midterm is more ambiguous than the second?
Or just
Yes.
Because the second midterm had more math problem, and the first midterm had more like reading and writing problems. So for most people, they'll probably be in computer science, it's probably better in math than reading and writing. So that's why most people are better at it.
All right. I'll think about it. Yes.
The class starts off with some rather esoteric concepts. Like you start with functions and relations and qualities of them that
Yeah.
kind of have these very abstract applications.
Yeah.
And we're, at least as students through like high school and up through the college courses, usually when a class starts off with esoteric concepts, but I think students expect the exams and quizzes to be kind of easy because it's not hard numbers that you're crunching, it's just these kind of wacky definitions, but you,
Yeah.
and not to say that it's wrong to necessarily hammer on those definitions, but I think as students, we're not used to expecting to know the rigorous definition of these esoteric concepts.
All right.
And
Thank
then,
you.
And then after we get a bad grade on the first midterm, we realize, oh crap.
Right. So can I throw this there? A big part of the first midterm is about Boolean expressions and sets that probably no one knows. Is it possible that people take this more lightly because they say, I know this one, and they prepare less, and maybe they prepare less on the more technical part of over the first time? Is it possible or not? Yes.
I have a different theory that it might have to do with, and I think you're dealing with a lot of things like set theory that people haven't necessarily seen before on the first midterm. The second midterm had a lot of things like probability that people may have seen in some form in like a statistics class and stuff like that.
All right. I almost thought the opposite because you go in set theory, but really we do union and intersection and
Right.
Cartesian product, but there is almost
Well,
nothing.
like even
It's not set
even
theory.
in early calculus class, you wouldn't necessarily see it, at least not written out like that.
All right. All
But
right.
you see probability in statistics class.
So my best bet the next time that I teach this one is to scare students about the first midterm and see whether they will do better. Yes.
I actually agree with what he was saying. It's like I've gone through like off one before, and I don't think that like I don't think I've seen those concepts in the beginning
All right.
like very well fleshed out at all. But it's just, like other concepts other than the word, like I totally seen that stuff before.
Alright.
So it's a lot more fun.
All right. Good to know. Yes.
I think one thing, so I did relatively well in the first midterm, and I think that one of the reasons I did like reasonably well was because it's not on your website's notes, particularly on relations and functions. We aren't used to seeing a function, so we can expect a function to have a set of inputs and a set of outputs.
Yes.
We're not used to seeing the function as a set itself, of the relation being sets of pairs of input and output, which isn't a huge thing, but I think it confused me, and then I had to like spend a few hours in the textbook, and then I was like, oh, that's strange.
So since you mentioned the textbook, how much do people like or hate this textbook?
do not like. I will claim that right there.
So students really hated the previous one because it was too long. And so I decided to pick the one that was short, and now they hate it because it's too short.
There's never going to be a good option for more.
So here is the problem, one size fits all. I mean, this is like a pair of pants. It's too long for someone. Sam, yes?
I think like part of that could be fundamental attribution error, like people like the textbook, but they also like tests. Maybe it's the test kind of catered more to the textbook. Does that make sense? And maybe like you also you like a lot more choice. It's a thing, I get that. Maybe it's like you got a matching section instead of a multiple choice for the definition. It might
Yeah.
be easier for people to quickly get through a set of 5 matches. You know, 2 sets of 5 matches, and that's the first 10 questions, and then the next 20 can be like math problems.
So, becomes subjective to grade that sometimes. So you get into this argument. Do they understand what you are asking or not?
I didn't hear you say.
So, half of the exam should be multiple choice. And the other half should be,
Like matching for definitions.
what do you mean matching?
Right?
Like 1, 2, 3, 4, 5, and A, B, C, D, E, and there's definitions and terms, and you match like, oh, A goes to like 3.
All right. Maybe possible.
Just
Like, is the above set bijective or conjective?
All right. If people look at this and they want to know some problem of this, we can on Wednesday we can look at other problems. If you want me to do a problem, try to make sure you can tell me why that one. What is not working for you? So I address really what is the problem rather than repeating it. All right. So where are we? Graphs. So of all the structures discrete structure that we have been discussing so far, graphs are by far the most complicated. So since now we are on schedule, we take it easy and we'll try to understand this well. So a graph is a pair. What does it really mean now that we have taken this class for 8 weeks? What does it mean that a graph is a pair? That there are 2 things, right? To tell you what is a graph, I have to tell you what is in the first slot of the pair and what is in the second slot of the pair, right? Instead of writing that way, I could write it. A graph consists of 2 pieces of information. Mathematicians say a graph is a pair. And the first is a set of elements. And when we talk about graph, these elements are called vertices or nodes. This is the usual story. When we talk about probability, these elements, how are they called? Points. Right? When we talk about languages or strings, how these elements, how are they called? Characters. It's always the same. So don't be fooled by the name. These are elements of a set. And E is a set of pairs of those elements. And so if I had to discuss this one written here, who can tell me what are the nodes and what are the edges? And I'll write them here. The set of nodes or vertices is what? Fantastic, you got it. And the set of edges is what? You have to look at this one, right? Who can tell me some edges? AD. BD. Oh, sorry. Yes, you can look at both. But basically you got it, right? So, when we discuss graphs, they come in two variations or two families. Some are called directed, because there is a direction. And the other one are called undirected, like this one. Here, there is no direction between AD or DA. They are just connected. So, if you consider a graph undirected, instead of a pair, you put a set there. So the set is A and B, and you don't tell whether you go from A to D or D to A. The element in the set have no order, so the set AD or DA is the same. If it is directed, AD means you can go from A to D, but not from D to A. There is a direction. Or you could go both if you have a. Basically, you can think about the streets of a city. If it is one way, you write it as a pair, where you start and where you end. If it is both ways, either you put both AD and DA, or you put them in a set. What is bad about putting in a set is that this is a set of two elements always. It's not any set you want. It has to be a set of two elements. Alright? And so, this is when the edges can be directed or undirected, and likewise the graph is said a directed graph or an underdirected graph. You with me? Alright. Sometimes the edges have an attribute or more than one attribute attached to them. This depends on the problem. If, for example, these represent the cities and flights between the cities, the weight could be the cost of the ticket, or could be the amount of time it takes, or the miles that they are distant, or something like that. And of course, this attribute could be a triple, where you put the cost, the time, and the miles. All right, and we call this weight. Graphs can have cycles. So here, in this graph that we have here, this is the graph, let me write it here. AD, BC. You could have a cycle like D goes to C, goes to A, and goes to D. Some people instead say that a cycle is something like from C you can go to C. For some problems this can make sense. For some problems it doesn't make any sense at all. You don't have a flight from Portland to Portland that you jump in the air and you come back.
So if that is one definition of cycle, what was the other one?
Right. So this also is called a cycle. This one A, D, C. All right. So we use it for both the concept, and when we use it, we make it clear that everyone knows how it's applied. Yes.
That version of cycle, not the reflexive for one.
Right. And this also is called a cycle.
Right. So not that one. The like A to D to C to D.
This also is called a cycle.
For that is that
Yes.
is that a characteristic of the type of graph, or is that just something you can do when you're very easily connected?
I think I'm missing the point.
Like, can you do that on any, like, it is following a cycle, is that an action done on a graph, or is that a characteristic?
Is an action done? More likely is an action you want to avoid. Because at some point you want to go to all the points of the graph. If you enter a cycle and you keep looping there, you are never going to get to the rest. So cycles typically are words. And something very good about the trees is that the trees don't have cycles. Trees are also directed. You go from a parent to a child. This is the intended direction of the tree. All right. You remember that when we talk about the trees, oops, you are not seeing it. You remember that when we talk about the trees, we had a terminology like a parent, child, ancestor, successor, sibling, things of this kind. And so here also we have a terminology to describe situations or relation in the graph. So one is adjacent node. Two nodes are adjacent if there is an arc or edge between the two. So if I bring back this one, who can tell me two adjacent nodes? And two nodes that are not adjacent. AD are adjacent, AB are not adjacent. Alright? So very clear, very simple concept. If you have an edge, there is an initial and a terminal node. This works only for directed graphs. If you look at the graph there, you don't know whether A is the initial and D is the terminal or the other way around. When we write a graph, if the graph is directed, then we put an arrow. And if the graph is weighted, typically we put the weight near the edge. And so the one that we see there perhaps is the most vanilla flavor of all, where there are no directions and there are no weights. Alright, so an edge is incident to a node or from a node. So let me change, let me see if I have here a directed one. I don't have any directed one. So let me change this that I have here into a directed one. How do I make this directed? I put arrows. So I put an arrow here, an arrow here, an arrow here, an arrow here, and an arrow here. You see the directions now? So this edge here is incident to which nodes? A. Means ends up in A. We say that this edge is incident to A. And the same edge is incident from D, because it's leaving D. This is just terminology. It's how we call these things. So a node has a degree, or perhaps has 2 degrees. If the graph is undirected, the degree of a node is the number of edges that go or leave from there. There is no notion of going or leaving, just are there. And so, what is the degree of D? 3. What is the degree of A? 2. Very good. If I go to this one, I have an in degree, which is the number of edges that are incident to a node, and there is an out degree. So what is the in degree of D?
2.
And the out degree? 1. So you got the concept. What is the in degree of C there? Well, I see 2 arrows ending there, right? So it's 2. And what is the out degree? 3. Because from C we go to C, which is 1, to D, which is 2, and to B, which is 3. Alright? Alright, so we look at the notion of edge incident to or from, degree of a vertex. If the degree is 0, how do we call that? That node isolated, because no one is going there, and from that node you don't go anywhere. Typically, this is not an interesting node in the graph because it doesn't play anything with the remaining node. So we want to toss it away. Pendant, if a degree 1, means it's the end of the line. Yes?
How can something be in a graph if nothing goes to it? It doesn't go
Well, because according to the definition, you can have it. If you remember the definition that we had, this is why definitions are important, and this is why considering extreme cases is important, because they really help you focus on the definition. So a graph is a pair where you have the nodes and the edges. So the set of edges could be empty. This is not an interesting graph, but the set of edges could be empty. So you have only the node, and they are all isolated. I don't know what you can do with that graph, but basically fits the definition. All right, so
What was the pendant part?
dependent is a node that no one goes there, and from the node you don't go anywhere. Oh, sorry, pendant. Yes, I thought isolated. Pendant, yes. So we can draw. Let me change this my graph here, and now I put something here that I call E. E is pendant because the degree of E is 1. Yes?
So if the arrow was pointing the other way, it would still be pendant?
Yes, because the pendant is basically is a concept that doesn't look at the direction. Yes?
So is pendant kind of like a leaf
In some sense, but it's not called a leaf. But
No,
yes,
it's not. So
it's
what's
not.
the
But
difference?
it is a similar concept. It's the
So-
end of the line.
So if we had another thing like Q that's pointing at E, would Q be considered a leaf? Or-
Yes,
or
so-
a pendant?
Right. If I put something here like a Q with an arrow here, E is no longer pendant.
But Q is.
Q is. All right. These are not difficult concepts, right? We just have name to describe a particular situations in a graph. And so we have a little bit of notation. If a V is a vertex or a node, deg with a minus is the number of edges that goes there. All right, we put with the minus. And plus are the ones that are going out.
So those are only for direct graphs.
Right. And we also have a dagger when it's undirected, or we don't care whether it is in or out. All right. So again, let's look at this example. So what is deg minus of A? Is 1. Why? Because there is only one edge that points to A. What is deg minus of D? 2, because there are 2 that go there, right? Now, if you consider all the degrees in a graph and all the edges in a graph, what do you expect? Every edge counts 1 degree for one node and 1 degree for another, right? There is no other way around. If you have an edge counter, whether you have them oriented, directed, or not. So, we have some theorem. Says if you have a graph and the graph is undirected, let's try to read this formula. Let's make it bigger so we focus on that. This one here. How do we read it? Twice the cardinality of E, so twice the number of elements in the set E, which are the edges, so twice the number of edges is equal to what? The sum over all the nodes of the degree of the node. Alright? So, this is a theorem. It's called handshaking. Someone has any idea why it's called handshaking? One hand is one edge and the other hand is the other edge. They have to meet here and they count 2 for the node. So let's go back to the example. Here, let's apply the theorem to this one, which is undirected. So, how many edges? 5. So, 5 times 2 is 10. Now, if you add the degree of all the nodes, you have to get 10. You see? We have 2, 3, 3, 2, which is 10. This is not a difficult theorem, right, to prove. How would you prove? You discover that the things in graphs, on the one hand, are completely obvious. This one that I'm telling you, you are totally convinced that this is true, right? Now, if you have to prove it, all of a sudden, it seems very difficult. How would you prove it? Yes?
You know that each edge has to have a pair, like it always goes from something to another thing. It's
Yeah.
a direct graph, right? Which means that there is essentially an arrow pointing to that object, and there's essentially a arrow pointing from that object to this one, right? So, self-explanatory.
Everyone can see it, right? That's a good proof. So I think you have to prove it by induction. You say, if I have a graph where this is true, if I add a node, or if I add an edge, what's going to happen? And then it remains true. So you can add all the nodes and all the edges that you want. So should we take a break and then we continue with these theorems? Good.